Hello, my name is Youn, and we will be presenting on our device, Motion Abnormality Detector, or MAD, which seeks to detect fall injuries prevalent in vulnerable populations. And by vulnerable populations, we are talking about senior citizens and people with physical disabilities such as ALS, paraplegia, and cerebral palsy. This is our agenda today. We will first start with the introduction by defining what the motion abnormality detector is and what we aim to provide with this technology. Secondly, development procedures, design and implementation. Thirdly, results and analyses, experimental procedures, conclusions, and limitations. Lastly, conclusion of our research as well as the summary of MAD and future possibilities. Introduction. Before getting into the details, here are some important facts we must address. According to the World Health Organization in 2021, falls are the second leading cause of unintentional injury deaths worldwide. This statistic is astonishing and incredibly tragic. Not only are falls the second leading cause of unintentional injury deaths worldwide, but each year an estimated 684,000 individuals die from falls globally, of which over 80% are in low and middle income countries. Additionally, adults older than 60 years of age suffer the greatest number of fatal falls. These statistics call for a solution to this massive health detriment that has been plaguing thousands across the globe, especially vulnerable populations. Around 50 million people worldwide suffer from epilepsy, 80% of which reside in low and middle income countries. Around 83% of epileptic patients have sustained injuries from seizures, and 1 in 1,000 patients die unexpectedly from seizures every year. With so many patients susceptible to seizures at any given moment, the need to detect abnormal motion is more pressing than ever. This is when MAD comes into picture. MAD hopes to provide not only a solution, but a vision. We want to provide an effective solution that can detect falls and alert guardians to provide immediate assistance and care within the golden hour. Falls could be slight physical injuries, but it can also be more serious, like faints and seizures. If not addressed, these injuries can lead to death. Providing immediate assistance is of utmost importance. This is why MAD's development and need is crucial. Utilizing computer vision and post-estimation techniques, MAD captures abnormal movement like falls, faints, and seizures that can be alerted to guardians. Unlike existing solutions which use sensors or wearable devices, our solution is purely based on computer vision software. Our system protects the client's privacy by transmitting motion detection without saving recorded data. Image data is erased from the device immediately without being sent to a server. We will now elaborate on our developmental procedures on creating MAD, including hardware and software design. Our hardware components consist of Raspberry Pi 4 Model B, Raspberry Pi monitor, mounted camera module. The devices and pictures above belong to our group mates. To carry out the MAD testing, we connect to the monitor to the Raspberry Pi and the camera module. This was then secured onto the wall in order to acquire live video from a living room environment. To make the most out of MAD, it is recommended to install the camera module on a wall that can detect the whole room without any obstruction. For software components, we utilize the OpenCV library to read and process live video from the Raspberry Pi's camera module. OpenCV is a commonly used Python library for projects associated with computer vision. Then we track recorded movements using the post landmark models from Google's machine learning library, MediaPipe. And this model detects 33 pose landmarks on the human body and produces data to track each respective body part. We decided to focus on the shoulder and hip when tracing human movement due to their visibility in most angles. Even if someone is wearing clothes or a blanket, the shoulder is usually exposed, making it a reliable body part to observe. MAD can track fall movements in comparison to ordinary movements. While creating MAD, we came up with clear definitions related to falls, faints, seizures, and recovery. This helps MAD to easily distinguish between these different situations. We took help from the University of Roseso's UR fall datasets consisting of 20 videos to evaluate the occurrence of potential falls. We considered the frame read by the camera as a 3D plane and studied the pattern and variations in shoulder and hip movements with respect to X, Y, and Z coordinates. Subsequently, we measured the acceleration of the shoulder over consecutive frames to detect potential falls. To make our MAD system only alert users of dangerous situations, we avoided detecting falls with recovery and a set time limit for falls and faints to prevent false alarms. We decided to concentrate on our efforts on the most common type of seizure, tonic-clonic seizure, because there are numerous types of this issue. But unfortunately, we couldn't find any data sets in the public domain that would help us formulate a heuristic rule. Thus, we only had to rely on our own definitions and the movements of the tracking shoulder to decide what it should be. And in the foreseeable future, we are looking to expand this project and collaborate with senior care centers and hospitals to acquire accurate data, constantly looking for ways to improve on what we have. The definitions that MAD defines are: a possible fall is a 50% increase in acceleration headed downwards in 0.5 seconds compared to the acceleration in the zero point 0.5 seconds before. A fall is minimal movement without recovery for continuing 5 seconds after a possible fall. A faint is considered minimal movement without recovery for continuing 20 seconds after a possible fall. A seizure is considered a 5 sign changes in difference every second for continuing 10 seconds. A recovery is when the shoulder height within the frame reaching 50% of its previous height before the fall, and the shoulder width changing 30% from the fall. These definitions are important to clarify in the experiment so that MAD can correctly identify what has occurred. Immediately after the situation has been detected, an alert will be sent to the guardians via Naver Cloud's platform's SMS API so that the individual can be immediately assisted. The guardian will receive notification of the detected scenario via text message. Would you like to continue, Wonjun?
Yeah, thank you. Okay, so now we'll elaborate on our results and analysis. After feeding 28 videos to MAD, it correctly deduced 25 videos false and scenarios appropriated. The experimentation yields a high 89% accuracy rate of MAD. Here is footage of MAD detecting possible falls. MAD, a system for detecting falls, was tested using 10 videos from the UR fall datasets. The footage of the test results shows MAD's ability to detect potential falls. After careful review, we identified 10 videos that might be categorized as false. However, since the data did not satisfy our criteria of a fall, which is 5 seconds after fall without potential recovery, they were only estimated as potential falls instead of actual falls. Here is footage of MAD detecting possible falls from various angles. We tested MAD's fall detection capabilities in a home setting with Raspberry Pi, and we fell at 8 different angles and stayed still for 5 seconds each to see if MAD was able to recognize the fall and send out an alert through a text message. As a result, the test was successful and it correctly deduced all 8 angles. Here is footage of MAD detecting seizures from the Epilepsy Foundation and Apollo Hospital's video. We performed a comprehensive search to collect videos for our MAD datasets. Although we created specific criteria for seizure classification, MAD was able to identify all of them accurately. Because the videos were limited to less than 10 seconds, we modified our baseline rule of having a jerky movement for at least 10 seconds to fit the duration of the video. However, tonic-clonic seizures generally last longer than 30 seconds, thus avoiding any possible complications. Even with the success of MAD's experimentation, we are still lacking in various regards that we hope to address. Firstly, we need further experimentation to avoid false positives and negatives. Throughout the experiments, we have encountered such situations, and with further research, we hope to reduce chances of false positives and negatives. Secondly, we need more video data to make conclusive results. We currently only have 28 videos, and while it is a successful first round of experimentation, good results are only reliable with further testing, and we are still testing for more possibilities. Third, despite video testing for seizures, there isn't only one type of seizure. We hope to further improve MAD's heuristic rule to define seizures by finding more video footage of seizures. Lastly, the technology of MAD could benefit from deep learning models. Deep learning models contain multiple layers of analysis and can exceed beyond human level performance. Using deep learning models can transform MAD and improve its prediction accuracy. With these limitations addressed, here are our next steps for MAD. MAD's focal message lies in the fact that prevention is health. Its potential to detect and aid those who have fallen or experiencing other fall-related injuries can save many lives if guardians are alerted of the situation immediately. Currently, MAD is proposed and experimented by our group in South Korea, but it can do so much more. With further research and collaboration with others around the world, it can be used by individuals worldwide. It can produce massive positive impacts on the rest of the globe beyond South Korea. In conclusion, we're aiming to expand the source code of MAD by producing video sets from hospitals and research facilities with the purpose of enhancing MAD's accuracy in diagnosing fainting seizures and falls. In order to enhance the precision of MAD, a larger number of videos need to be utilized. Following this, we must train a deep learning model to augment its accuracy rating even further. We humbly accept that we're merely high school students, and while our enthusiasm for MAD is immense. Involving professionals in the field with more experience can drive MAD to its full potential. Our mentors and teachers have been instrumental in helping us understand the subject better. Collaboration is key to truly improve MAD. Thank you, and if you have any questions for us, we would be glad to answer them. 감사합니다.